Today we're going to talk about 1 gigahertz and greater frequency testing. EMC for Product Design is a book by Tim Williams. I read it a lot for doing the emissions and immunity testing, helping my customers solve problems, and it's a great writer. It's a very reasonably priced book. I think you should buy it. Everybody should have one. Normally, when we do the emissions testing with commercial products, or even COTS, commercial off-the-shelf products, the frequencies that we're concerned about are less than a gigahertz. It's just recently that people are interested in gigahertz for whatever new developments are out there. But more specifically for military applications and radio applications, there is an extreme interest in gigahertz or greater noise. So Tim Williams talks about horn antenna for measuring frequencies above gigahertz. These things are based on MIL standards 461G, radiated emissions in the 1 to 18 gigahertz range. And there's a setup that we can use to measure frequencies measure high gigahertz frequencies using a Valdi horn antenna is specified by the MIL standards, but one of these flat antennas is what someone let me use here today. So we're gonna use this antenna to measure noise in the gigahertz range. So today I have the Copley R21. This is the ruggedized ACJ servo amplifier. The Valdi antenna with a short length to the amplifier, powered by 5 volts. 50 ohm coax cable connected to the Agilent spectrum analyzer. The frequency of interest is 1.44 gigahertz. I've got the reference set and 3 decibels per division here so that we can see a significant jump in the amplitude. The span is 10 megahertz. The resolution bandwidth 100 kilohertz. The VBW also 100 kilohertz. And I got a 3.1 millisecond sweep here. So that's how the function generator was set up. So you can push the buttons to set things up. And what we noticed with this drive was just even with the power connected, we saw a bump up from the baseline. So, one way to measure, how much noise there is at a certain range is not to look for necessarily a spike, but watch the whole ground level come up. So what we're going to do is monitor when the power is turned on, the increase in the noise. So the antenna is typically moved around to find the most effective place to measure the noise. So one thing we're going to look at here are ways to minimize the noise. So your hand will reduce it. An interesting phenomena I noticed here with this drive was, this is the commercial version of the same drive. It has the exact same circuit, but the effect of the radiation is not directed. So we need to take a look at the difference in these 2 drives. They're both the exact same circuit, but the cover here has a coppery looking metal surface coating on the inside. And I presume what's happening here is with the 1.44 gigahertz, you're talking like an 8-inch wavelength, a 4-inch half wave, and maybe a 2-inch quarter wave. So this can act like a cavity resonator. There's a good metal plate on the back, but the noise seems to come out the bottom, the front, and the top. So there's the radiation directions maybe cavity resonating and squirting out, or maybe even being conducted by the material. So the first recommendation is to get away from the metal coating and allow the radiation to expand rather than to be directed. The second recommendation here came from the principal engineer at Analogic, Ahmed Hussein, and he found some lossy foam. So this is the lossy foam. It's a black material. It looks like a kind of a sponge, and it's really good for absorbing gigahertz frequency ranges. Typically for EMS we use a metal shield, but this may not necessarily dampen out the signal. It probably just redirects it. So like a nice shiny mirror, it reflects the emissions. So there is an effect if we remove and replace, but this is not necessarily the only solution here. The recommendation is for the metal case surrounding the drive, or like the commercial version cover, or the cover without. Well, the recommendation is to have the lossy foam applied to the surface cage, so kind of like a Faraday cage with a bunch of absorbing materials so that nothing leaks out of it. So the ground level is pretty flat when we do both, and I was unable to measure much of a change, but I believe this would be the best conditions would be the plastic cover on the drive with no metal to act like a cavity resonator, surrounded by the foam, and then surrounded by the metal case. So we'll take a quick look at the lossy foam. This is the MF22, and it's Mass Technologies. We can see that the frequency losses at the gigahertz range is substantial. So the foam is one of the most effective ways to dissipate the radiation. There is also a recommendation for ferrites on the cables coming in and going out. Laird is another manufacturer of gigahertz materials. They may have their own lossy foam too. I think that's where I first saw the recommendation for the foam in the cover. You can see at the high frequency ranges there's significant impedance. This also has other 100 megahertz properties too, but these ferrites are designed specifically for the higher frequency ranges. And there's another clamp-on that has a smaller diameter hole. So again, Laird is a good. I'm still waiting to receive these, but they're on order. So to wrap up here, we've got a drive and an antenna, and we're trying to measure some of the gigahertz noise coming out. There may be a little bit of activity still in this drive, but again, significant radiation when we start putting metal material inside the cover. So my recommendation will be to make the ruggedized drive still, but change the cover to the blue style that does not have the coatings on the inside. Okay, thanks for watching.